It operates invisibly inside nearly everything we touch, from enterprise data centers and scientific supercomputers to laptops, game consoles, and the mobile phones in our pockets. Java powers a vast ecosystem of modern devices. This chart reveals the professional demand behind that reach. Among popular languages, Java stands out with 64,000 job postings and an average salary of over $100,000. To understand why it carries this value, we have to look at how computers actually work. At the hardware level, machines only understand binary, a stream of ones and zeros. Humans, however, need higher-level languages to communicate complex ideas, and reconciling these two worlds is difficult. Writing a language that feels natural to a human developer, yet executes with perfect machine precision, is a puzzle that has defined the evolution of computer science. The professional demand we see today stems from how Java manages this translation across an entire global infrastructure. Early structured programming followed a strict path. The code executed instruction by instruction, one after the other, in a rigid sequence that couldn't easily deviate or jump to different tasks. But the real world isn't a single rigid line. It's a chaotic environment filled with independent entities constantly interacting with each other. Object-oriented programming, or OOP, provided a solution. Instead of a single list of instructions, it treats a program as a collection of connected objects that communicate by sending messages to one another. Java was built on this OOP model, changing the way software is developed by allowing programmers to build code that finally mimics real-life logic. To see how Java digitizes reality, we can model a physical transaction, like a digital coffee shop. We start with variables. These are simply named locations in the computer's memory used to store specific details about our order. We assign primitive data types to these variables based on what they hold. We use an integer, or int, for the number of cups, and a decimal called a double for the price. We also use a Boolean for true or false states, and an object reference type called a string to store the customer's name. By declaring these specific variables and data types, the programmer has successfully captured the static properties of a physical object in a digital format. But data alone is static. To create action, Java uses methods. These are the verbs of the language, collections of code that perform specific tasks on our variables. Inside these methods, we use mathematical operators. By using the multiplication operator, the method can process the price and quantity variables to calculate the total cost of the order. These operators work on text, too. Through string concatenation, the plus operator can stitch together text and variables to print a final receipt, such as order for, followed by the customer's name. Methods and operators are the core engines of the application, transforming stored data into a dynamic, functioning interaction. We can also add logic through flow control. An if-else condition allows the program to branch. If a loyalty card is present, apply a discount, else charge the full price. Once the logic is written, we face a daunting deployment hurdle. How does this exact same code run on a Windows PC, an Apple iPhone, and a Linux server? Java solves this with a two-step translation. The Java compiler turns the human-written .java file into an intermediate .class file, known as bytecode. Then, the real hero, the Java Virtual Machine, JVM, sits on the destination device. It reads that universal bytecode and executes it specifically for that operating system. The JVM effectively decoupled software from the hardware it runs on, saving developers from having to rewrite apps for every new device on the market. This architecture achieved the ultimate goal of the era: write once, run anywhere. By pairing a language that mimics reality with a universal translator, Java provided a fix for the pervasive computing fragmentation of the 1990s. These syntax rules and methods are engineered bridges. They are the tools that connect human problem-solving to machine execution. Mastering these fundamentals provides the logic needed to build future infrastructure, providing the technical foundation for the high-paying career paths that sustain the modern industry.